In 1983, a man who had helped Stephen Hawking prove that black holes have no hair sat down and did something he immediately wished he had not done. He ran a calculation, not a complicated one, the kind of thing a first-year statistics student could follow. He took the estimated number of human beings who have ever been born, roughly 70 billion at the time, and he asked a question that sounds almost childish in its simplicity. If you were randomly plucked from the full lineup of every human who will ever live, from the first Homo sapiens to the last, what does your position in that lineup tell you about how long the lineup is? The answer should have been nothing. It should have been a parlor trick, a philosophical curiosity, the kind of thing you raise at a dinner party and then forget about. But Brandon Carter was not a dinner party philosopher. He was one of the most technically rigorous mathematical physicists of the 20th century. He had derived the fourth constant of motion for particles falling into rotating black holes. He had co-developed the diagrams that Roger Penrose uses to map the causal structure of spacetime. He had proposed the anthropic principle at a symposium in Krakow in 1973, on the 500th anniversary of Copernicus's birth, and the irony of that timing was not lost on anyone. Copernicus told us we are not special. Carter's principle said our existence constrains what we can observe about the universe. Both are true, and both lead somewhere uncomfortable. So when Carter ran the numbers on what your birth rank implies about humanity's total lifespan, he trusted the math, and the math said something he could not bring himself to publish. Here is what it said. Approximately 117 billion human beings have ever been born. You are one of them. The Doomsday argument, as it came to be called, asks you to treat yourself as a random sample from the total population of all humans who will ever exist. If the human species is going to produce, say, 200 trillion people over its full lifespan, colonizing galaxies and thriving for millions of years, then your birth rank of roughly 117 billion puts you absurdly early in the sequence. You would be in the first 0.06% of all humans who will ever live. That is like drawing a lottery ticket and getting number 58 out of 100 million. Possible. But you would not bet on it. Now consider the alternative. If the total number of humans who will ever live is closer to 200 billion, your birth rank is perfectly ordinary. You are somewhere in the middle of the lineup, which is exactly where a random sample should be. The Bayesian math is merciless. Even if you start with only a 5% prior probability that humanity ends relatively soon, the update from your birth rank shifts that probability to 98%. The likelihood ratio is 1,000 to 1. The calculation is not complicated. It is not ambiguous, and it has survived every serious mathematical objection thrown at it for 4 decades. Carter never wrote it up for a journal. He presented it in lectures, in seminars, in private conversations. The idea passed through the academic ecosystem, the way uncomfortable truths usually do, through whispers. It was the philosopher John Leslie who finally brought it into print, with Carter's written permission in a letter dated May 28, 1989. Leslie spent years defending and elaborating the argument, eventually publishing The End of the World in 1996. But the result was always Carter's, and Carter's silence about it tells you something important. This was not a man who shied away from controversial ideas. He had challenged the entire framework of observational cosmology with the anthropic principle. He had worked in the most abstract reaches of general relativity. He was comfortable with ideas that made other physicists uneasy. But the Doomsday argument was different. It was not about the structure of black holes or the geometry of space-time. It was about an expiration date. And it was about you. 10 years after Carter's private revelation, a Princeton astrophysicist named J. Richard Gott III independently arrived at the same territory through a completely different route. Gott called his version the Copernican method, and unlike Carter, he was not shy about publishing it. His paper appeared in Nature on May 27, 1993, Implications of the Copernican Principle for Our Future Prospects. The title was dry, the contents were not. Gott's approach was elegant. If there is nothing special about the moment you happen to observe something, you can derive prediction intervals for how much longer it will last. His formula says, the future lifetime of anything you observe lies between 1/39th and 39 times its current age, at 95% confidence. Apply to Homo sapiens, a species approximately 200,000 years old. This gives a future lifespan of between 5,160 years and 7.8 million years. That sounds like a wide range, but notice what it excludes. It excludes the galactic empire. It excludes the trillion-year future. It excludes the assumption that we are at the very beginning of something enormous. The math says we are probably somewhere in the middle of the story. And the middle of the story, for a species, means the ending is closer than you were taught to believe. Gott had tested this method before publishing it, and the test is one of the most remarkable predictions in the history of probability theory. In 1969, as a 22-year-old Harvard graduate traveling through Europe, Gott visited the Berlin Wall. It was 8 years old. He had no special information about geopolitics, no inside knowledge of Soviet intentions, no expertise in international relations. He simply applied the Copernican principle. The wall had existed for 8 years, so with 50% confidence, its future lifespan was between 2.67 years and 24 more years. It would fall sometime between 1971 and 1993. The Berlin Wall fell on November 9th, 1989, 20 years after Gott stood in front of it, squarely within his prediction. On the day his Nature paper was published, Gott tested the method on all 44 Broadway and off-Broadway shows then running, predicting 95% confidence intervals for each show's closing based solely on how long it had already been running. Of the 36 that had closed by the time he checked back, every single one fell within his predicted interval. Every one. The Doomsday argument has its critics. Dennis Deeks published a rebuttal in 1992 arguing that your very existence is more likely in a universe with more people, which exactly cancels the Bayesian shift. Nick Bostrom, who would later become the most influential philosopher of existential risk, formalized the debate in his 2002 book Anthropic Bias, distinguishing between the self-sampling assumption, which supports the Doomsday argument, and the self-indication assumption, which neutralizes it. Bostrom argued against the self-indication assumption through what he called the presumptuous philosopher problem, where a philosopher could override empirical cosmology through pure armchair reasoning. But he ultimately called the Doomsday argument inconclusive. Inconclusive, not wrong, not refuted, inconclusive. After 4 decades, the best that the sharpest minds in philosophy and mathematics can say about a calculation that predicts humanity's relatively near-term extinction is that they cannot conclusively prove it is wrong. And here is the part that should keep you up at night. If the Doomsday argument applies to us, it applies to every civilization that has ever evolved intelligence anywhere in the observable universe. Every one of them had a birth rank. Every one of them could have run this calculation. And for every one of them, the math would have said the same thing. You are probably not at the beginning. You are probably near the middle. And the middle means the end is closer than it looks. That thought might seem like a stretch, a philosophical extrapolation with no empirical grounding. But the Doomsday argument is not the only mathematical framework producing this answer. It is not even the most disturbing one, because in 1961, 22 years before Carter's private revelation, a young astronomer in West Virginia wrote an equation on a chalkboard. And when you solve that equation with modern numbers, and then compare the answer to what we actually observe in the sky, the result is not just disturbing, it is confirmed. The morning of November 1st, 1961 was cold in the mountains of West Virginia. 10 men gathered at the National Radio Astronomy Observatory in Green Bank, a facility chosen partly for its remoteness. No cell towers, no radio stations, no microwave ovens, the quietest electromagnetic spot in the eastern United States. They had come to discuss a question that most of the scientific establishment considered slightly embarrassing. Is anyone else out there? And if so, why have we not heard from them? The meeting was organized by a 31-year-old astronomer named Frank Drake, who had, the previous year, done something no human being had ever done before. He had pointed an 85-foot radio telescope at another star and listened. Project Ozma, named after the princess of the land of Oz, a character from a land far away and difficult to reach, and populated by strange beings, targeted two nearby sun-like stars, Tau Ceti and Epsilon Eridani, at the 21-centimeter hydrogen line, the frequency at which neutral hydrogen radiates naturally, and which any technologically sophisticated civilization would know to monitor. The total budget was approximately $2,000. Drake had convinced the observatory director, Otto Struve, to allocate telescope time by arguing that even a negative result would be scientifically valuable. Struve, a Ukrainian-born astronomer who had spent his career studying binary stars and stellar rotation, agreed on the very first day of observation, April 8, 1960. Pointing at Epsilon Eridani, the team detected a signal, pulsing, regular, 8 beats per second, perfect periodicity, the kind of pattern that cannot be produced by natural astrophysical sources. Drake's heart rate doubled. The technicians looked at each other for a few minutes in a small control room in rural West Virginia. A handful of people believed they might be witnessing the most important discovery in human history. Then they moved the telescope away from the star, and the signal persisted. It was coming from a high-altitude military aircraft that nobody was supposed to know about, almost certainly related to Cold War surveillance. The first SETI experiment ended with a classified false alarm. Drake would later call it a useful lesson in premature excitement. But years later, he admitted that those few minutes had changed something in him permanently. He had felt, however briefly, what it would be like to know. But Drake had a problem. He needed to organize the Green Bank meeting, and a few days before the conference, he realized he did not have an agenda. So he sat down and asked himself what you would need to know in order to estimate how many detectable civilizations exist in the galaxy right now. He wrote down each factor, and then he realized that if you multiplied them all together, you got a number. One number. the number of civilizations in the Milky Way that we could, in principle, detect at this moment. On the morning of November 1st, Drake walked to a chalkboard and wrote 7 symbols that would frame humanity's search for cosmic company for the next 6 decades. N equals R star times FP times NE times FL times Fi times Fc times L. The rate of star formation multiplied by the fraction of stars with planets, multiplied by the number of habitable planets per system, multiplied by the fraction that develop life, multiplied by the fraction that develop intelligence, multiplied by the fraction that produce detectable technology, multiplied by the length of time those civilizations remain detectable. The 10 attendees, who later dubbed themselves the Order of the Dolphin, after neuroscientist John Lilly's research on dolphin communication, included a 27-year-old Carl Sagan, the youngest and least distinguished person in the room. They also included Melvin Calvin, a biochemist from Berkeley, who received a phone call during the conference informing him that he had just won the Nobel Prize in chemistry. Calvin, in his post-Nobel euphoria, later had silver dolphin lapel pins made from an ancient Greek coin design and mailed one to each participant. At the close of the meeting, Observatory Director Otto Struve raised a glass and offered a toast that echoes through every subsequent decade of this story. To the value of L, he said. May it prove to be a very large number. L, the longevity of a technological civilization. Struve understood, in that single toast, that the entire equation collapses into one variable. Everything else is astronomy and biology. L is the only factor that depends on whether civilizations survive their own technology. Drake's original estimates were necessarily rough. He guessed 1 star forms per year, that 20 to 50% have planets, that 1 to 5 of those planets would be habitable, and that life, intelligence, and technology would emerge on essentially all of them, given enough time. For L, he offered a range from 1,000 to 100 million years. With optimistic values, the equation produces tens of thousands of civilizations in our galaxy right now. With pessimistic values, the answer could be as low as 1. Us, alone. In the 6 decades since Green Bank, we have pinned down the astronomical terms with extraordinary precision. The Kepler Space Telescope, launched in 2009, revolutionized our understanding of planetary frequency. We now know that virtually every star has planets. The fraction Fp is not Drake's cautious 0.2. It is effectively 1. A November 2013 analysis of Kepler data estimated 40 billion Earth-sized planets orbiting in the habitable zones of Sun-like and red dwarf stars in the Milky Way alone. 40 billion chances for life in one galaxy. And there are 2 trillion galaxies in the observable universe. But here is where the equation turns dark. The 3 biological terms, the fraction of habitable planets that develop life, the fraction that develop intelligence, and the fraction that develop detectable technology, remain almost entirely unconstrained. They could each be close to 1, in which case the galaxy should be teeming with signals, or any one of them could be vanishingly small, in which case we are alone. As Jill Tarter, one of the most distinguished SETI researchers in history, said of the Drake equation, that it is a wonderful way to organize our ignorance. But the equation does something else, something its creator did not fully intend. It sets up a prediction. If you plug in even moderately optimistic values for the biological terms and a reasonable estimate for L, the number N comes out in the thousands. There should be thousands of detectable civilizations in the Milky Way. We have been listening for over 60 years. We have heard nothing. That silence is not an absence of data. It is data. And it was a physicist named Enrico Fermi who first grasped what it means. In the summer of 1950, 4 physicists walked lunch at the Fuller Lodge cafeteria at Los Alamos National Laboratory. Enrico Fermi, Edward Teller, Emil Konopinski, and Herbert York. They had been discussing a cartoon by Alan Dunn in the May 20th issue of The New Yorker, depicting little green men stealing garbage cans from a Manhattan sidewalk, a humorous connection between the contemporary mysteries of flying saucer sightings and disappearing trash. The conversation turned to interstellar travel. Teller estimated the probability of achieving faster-than-light travel within a decade at 1 in a million. Fermi, famous for his ability to estimate anything from first principles, disagreed. More like 10%, he said. Then they sat down to lunch. The conversation moved on to other things. And then, without preamble, in the middle of the meal, Fermi blurted out a question. The 3 surviving participants each remembered it slightly differently. Teller recalled, "Where is everybody?" York remembered, "Don't you ever wonder where everybody is?" Konopinski recalled, "But where is everybody?" The result, according to Teller, was general laughter, because everybody at the table understood immediately that Fermi was no longer talking about garbage cans. He was talking about extraterrestrial life. Fermi then did what Fermi always did. He made rapid calculations on the back of an envelope, and he concluded that Earth should have been visited long ago and many times over. Fermi died of stomach cancer in 1954 at the age of 53. He never published on his lunchtime question. The physicist Eric Jones reconstructed the conversation in 1984 by writing to the 3 survivors. The first print appearance was a footnote in a 1963 Carl Sagan paper. The term Fermi Paradox did not enter use until around 1977, but the paradox itself has only sharpened with time. Michael Hart formalized it in 1975, calculating that even at 1/10 the speed of light, a single civilization could colonize the entire Milky Way in roughly 2 million years. That is a cosmic eye blink. The galaxy is over 13 billion years old. If even one civilization anywhere in its history had developed interstellar travel, their descendants would be everywhere by now. Frank Tipler extended this in 1980, arguing that self-replicating probes could explore every star system in the galaxy in under 300 million years. You do not even need crude ships. You need one machine that can copy itself. Sagan and Newman pushed back in 1981, arguing that Hart's expansion rates were unrealistic. But even with deliberately conservative assumptions, the colonization timescale is a small fraction of the galaxy's age. The math always comes back to the same place. They should be here. They are not. And this is where a viewer's comfortable assumption usually steps in. The Fermi Paradox has lots of solutions, people say. Maybe they are hiding. Maybe they are watching us from a distance, the zoo hypothesis. Maybe they are deliberately quiet because the universe is dangerous. The dark forest theory from Lou Chitzin's science fiction. Maybe we live in a simulation, and the programmers did not bother coding aliens into our particular run. Maybe intelligent life is common, but nobody bothers with interstellar travel because the distances are too vast and the energy costs too high. These are not solutions. They are stories, and they fail quantitatively. The zoo hypothesis requires that every civilization in the galaxy's history, across billions of years and hundreds of billions of stars, independently decides to leave Earth alone. Not one defector, not one rogue explorer, not one automated probe drifting into our solar system over 13 billion years. The coordination problem is staggering. The dark forest theory requires that civilizations destroy each other on detection, which means the galaxy should show signs of cosmic warfare, energy signatures, destroyed star systems, Dyson sphere remnants. It shows none. The simulation hypothesis is unfalsifiable and therefore not a scientific explanation. And the distances are too vast. Objection ignores self-replicating probes entirely. You do not need to cross the galaxy in one trip. You need to build one machine that lands on a nearby star system, mines resources, builds copies of itself, and sends them to the next stars. Exponential growth handles the rest. 300 million years, tops. When you eliminate the comfortable answers, you are left with the uncomfortable ones. And the most uncomfortable answer is the one that connects the Fermi Paradox directly to Carter's Doomsday argument, directly to Drake's equation, and directly to a number that an Oxford philosopher would publish in 2020 that should have made front-page news around the world, and did not. Something is preventing civilizations from becoming detectable. Something is filtering them out. And in 1998, an economist with 9 years of AI research experience at NASA and Lockheed sat down and gave that something a name. Robin Hanson is not the person you would expect to produce one of the most important ideas in the history of existential risk. He is an economist at George Mason University. His PhD is in social science from Caltech. Before academia, he spent 9 years doing artificial intelligence research at Lockheed and NASA. He is better known in some circles for his work on prediction markets than for anything related to the fate of intelligent life in the universe. But in 1998, Hanson published an essay on his personal website that reframed the Fermi Paradox as a statement about our future rather than a puzzle about the past. He called it the Great Filter. The argument is simple and devastating. Between dead matter and a galaxy-spanning civilization, there are many steps. Hanson listed 9. The right kind of star system with organic chemistry, reproductive molecules like RNA, simple, single-celled life, complex, single-celled life, sexual reproduction, multicellular life, tool-using animals with large brains, the stage we are at now, and finally, a colonization explosion visible across the galaxy. The Great Silence, the fact that we observe zero evidence of galactic civilizations despite the Drake equation predicting thousands, means that at least one of these steps must be astronomically improbable. Something along this path is filtering out almost every attempt. The product of all the probabilities across all 9 steps must be very, very close to zero, because the observable result is 0 civilizations detected. Now here is Hanson's insight, and it is the kind of insight that, once you understand it, restructures how you think about every piece of good news in biology and astronomy. Optimism about the early steps is directly pitted against optimism about our future. If the first 7 steps are relatively easy, if life emerges frequently, if intelligence is a common outcome of evolution, if tool use is a natural progression, then the filter cannot be behind us. It must be ahead. Something at step 8 or step 9, something that happens to civilizations at roughly our stage of development, destroys them with near-perfect reliability. But if the filter is behind us, if one of the early biological steps is so fantastically unlikely that Earth is essentially the only place it ever happened, then the cosmos is empty because we are the only ones who made it this far. Our future could be bright. The price of that optimism is accepting that we are alone in a way that is almost incomprehensible. The only minds in a universe of 2 trillion galaxies. You cannot have it both ways. Either life is common and civilizations are doomed, or life is vanishingly rare and we are a miracle. The evidence has been trending in one direction, and it is not the comfortable one. Every exoplanet discovery, every extremophile found thriving in boiling acid or frozen Antarctic lakes, every amino acid detected in interstellar gas clouds pushes the biological terms in the Drake equation upward. Life seems to be easy. Chemistry wants to become biology. And if that is true, the filter is not behind us. It is ahead. Nick Bostrom crystallized this implication in a 2008 essay for MIT Technology Review. The title was, "Where Are They? Why? I hope the search for extraterrestrial life finds nothing." His argument was that finding even simple microbial life on Mars would be terrible news for humanity, because it would mean the early steps, the formation of life from chemistry, happened independently at least twice in one solar system. If it happened twice here, it probably happened billions of times across the galaxy. And if life is that common, the great filter cannot be the origin of life. It must be something else, something later, something ahead. Bostrom's conclusion was stark. He argued that in the search for extraterrestrial life, no news is good news. Every discovery that makes the universe seem more hospitable to life makes the future of civilization seem more fragile. The emptier the sky, the safer we are. And the sky is very, very empty. But even if the filter is ahead of us, how dangerous is it? How close are we? Is this a theoretical concern for civilizations 10,000 years more advanced than us? Or is it something happening right now, in this century, to a species that has only had nuclear weapons for 80 years? In 2020, a philosopher at Oxford published an answer, and the answer was a number. Toby Ord did not come to existential risk through cosmology or physics. He came through ethics. Born in Melbourne in 1979, Ord studied computer science before switching to philosophy. He completed his doctoral thesis at Oxford under Derek Parfit, one of the most influential moral philosophers of the 20th century. A man obsessed with questions about what we owe to future generations. Parfit's influence on Ord was profound and specific. If the future matters, if the people who will exist in 100 years have moral weight comparable to the people alive today, then preventing human extinction is not just important. It is, by a staggering margin, the most important thing anyone could ever do. The math is simple. If humanity survives, trillions of people could eventually exist. The expected value of extinction prevention dwarfs every other cause. Ord took this seriously in a way that most philosophers do not. In November 2009, he co-founded Giving What You Can with his colleague Will MacAskill and his wife Bernadette Young, a medical doctor. Members pledged to donate at least 10% of their lifetime income to the most effective charities they can find. Ord himself went further. He capped his salary at £18,000 a year and pledged to donate approximately £1 million over his career. By late 2019, he had donated £106,000, 28% of his income. This is not a man who treats moral philosophy as an abstraction. He reorganized his entire financial life around the mathematics of doing the most good. Then he spent years researching the probability that humanity destroys itself. The result was the Precipice, Existential Risk and the Future of Humanity, published by Bloomsbury in March 2020, weeks before the world locked down for a pandemic that would underscore every argument in the book. Ord's central claim is that humanity faces approximately a 1 in 6 chance of existential catastrophe this century. 1 in 6. The odds of Russian roulette, the roll of a single die. And unlike Carter's philosophical argument or Gott's statistical extrapolation, Ord provided a table, a specific, categorized, peer-reviewed breakdown of where the danger comes from. Table 6.1 in the Precipice is, I would argue, the most important table published in any book in the 21st century, and almost nobody has seen it. Asteroid or comet impact, 1 in a million per century. Supervolcanic eruption, 1 in 10,000. Stellar explosion, 1 in a billion. Total natural existential risk, all sources combined, comes to approximately 1 in 10,000 per century. Nature is not trying to kill us, not on any time scale that matters for planning purposes. The dinosaurs were unlucky. We have telescopes. Then the human-caused risks. Nuclear war, 1 in 1,000. Climate change, 1 in 1,000. Other environmental damage, 1 in 1,000. Naturally arising pandemics, 1 in 10,000. These numbers are concerning but manageable. The probability of any individual threat ending civilization is small. But then the table takes a turn. Engineered pandemics, 1 in 30. Not 1,000, not 10,000, 30. A 3% chance this century that someone engineers a pathogen that ends civilization. Ord considers this the second most dangerous category of existential risk. And at the top of the table, the entry that drew the most attention and the most criticism and the most quiet agreement from the people who actually work on this problem. Unaligned artificial intelligence. 1 in 10. A 10% chance in Ord's assessment that artificial intelligence that does not share human values causes an existential catastrophe within the next 80 years. Unforeseen anthropogenic risks, 1 in 30. Other anthropogenic risks, 1 in 50. Total anthropogenic existential risk adds up to approximately 1 in 6. Look at those numbers. Really look at them. The natural risks add up to 1 in 10,000. The human cause risks add up to 1 in 6. We are not in danger from the universe. We are in danger from ourselves. And the danger is not evenly distributed across categories. It is concentrated in technologies that did not exist 100 years ago and that are advancing faster than any institution's ability to regulate them. Ord is transparent about his methodology. For natural risks, geological and astronomical records provide hard constraints. 95% of near-Earth asteroids larger than 10 kilometers have been catalogued. We know the impact frequency. We can calculate. For anthropogenic risks, the methodology is, in his words, necessarily more subjective. Ord begins with a Bayesian prior, then updates based on scientific evidence, expert judgment, and historical data. He acknowledges the numbers could be off by a factor of 3 in either direction. He has said publicly, don't take these numbers to be completely objective. Their purpose is to show the right order of magnitude. His critics have seized on this subjectivity. Seth Baum, writing in Risk Analysis in 2022, called the estimates the subjective judgments of a single individual, among the least rigorous ways to quantify uncertainty. A review in the Notre Dame Philosophical Reviews suggested that depending on how skeptical you are, the total risk could be as low as 1 in 1,000 instead of 1 in 6. The London School of Economics critiqued the methodological opaqueness of the anthropogenic estimates. These are fair criticisms, and they expose a genuine mathematical problem that goes far deeper than Ord's particular estimates. The problem is fundamental. How do you calculate the probability of an event that has never happened? In 1774, Pierre-Simon Laplace proposed what became known as the rule of succession. If you have observed an event succeed on every one of n occasions, the probability it succeeds on the next occasion is n plus 1 divided by n plus 2. For events that have never occurred, the formula gives 1 divided by n plus 2. Applied crudely to nuclear war, 80 years of 2 nuclear powers without a full exchange gives a probability of roughly 1 in 82 per year. Crude, but it captures something real, and the number is in the same range as the more sophisticated estimates from Hellman and Barrett. But there is a deeper problem, and it is one that Ord himself, along with Toby Hillebrand and Anders Sandberg, identified in a 2010 paper in the Journal of Risk Research. They called it meta-uncertainty. If a scientific analysis A concludes that the probability of catastrophe is extremely small, the probability that analysis A itself contains a hidden crucial flaw may easily exceed the assessed probability. Most of the real risk does not live in the probability estimate. It lives in the uncertainty of the estimate. The formula is straightforward. The total probability of catastrophe equals the probability that the analysis is correct, times the assessed risk, plus the probability that the analysis is flawed, times the risk given the flaw. And the second term almost always dominates the first. This is why existential risk estimates range so widely. It is why Ord's 1 in 6 and the critics' 1 in 1,000 can both be defended. The uncertainty is not about the math. The uncertainty is about whether the math has correctly identified all the relevant variables. And for risks that have never been realized, there is no way to calibrate. But consider what even the critics' most conservative estimates mean. If you accept every objection, if you divide Ord's estimate by 6 and use the lower bound of 1 in 1,000, you still get a 1 in 1,000 chance of human extinction this century. Put that in context. That is still orders of magnitude more dangerous than any previous century in human history. A 1 in 1,000 annual probability of an airliner crashing would ground every fleet on Earth. A 1 in 1,000 chance of a nuclear plant melting down would shut down every reactor. A 1 in 1,000 probability that everything ends, that everything you have ever known or loved or built is erased permanently, and the response from the institutions that are supposed to protect you is a collective shrug. The critics argue Ord's numbers are too high. They do not argue the numbers are low enough to ignore. They cannot, because even their own numbers are terrifying for a species that has never experienced the event in question and would not get a second attempt. And here is what none of the critics address. Ord's table and Hanson's great filter are measuring the same thing. Ord is quantifying the filter from inside it. He is standing at step 8 on Hanson's ladder and calculating the probability that we fall. Hanson is looking up the empty sky and inferring that almost everyone falls. They did not coordinate. They did not compare notes. They arrived at compatible answers through completely different methods, Using completely different data, Ord sees a 1 in 6 chance of catastrophe this century. Hanson sees a universe that should be full of civilizations and is not. These are not two observations. They are two measurements of the same phenomenon, taken from different distances. Think about that. An economist looking at the empty cosmos and a philosopher looking at the probability tables are converging on the same conclusion. And neither of them is the Astronomer Royal of England, who arrived there first and stated it more bluntly than either of them ever has. Martin Rees, Baron Rees of Ludlow, was born in York in 1942. He became Astronomer Royal in 1995, President of the Royal Society in 2005, Master of Trinity College, Cambridge in 2004. He has published over 500 peer-reviewed papers. He has been knighted. He has won the Crayford Prize, the Wolf Prize in Physics, and the Templeton Prize. He is, by any measure, one of the most decorated and respected scientists alive. In 2003, Rees published a book called Our Final Hour. The subtitle in the American edition was A Scientist's Warning: How Terror, Error, and Environmental Disaster Threaten Humankind's Future in This Century, on Earth and Beyond. The subtitle in the British edition was Calmer. The contents were not. Rees claimed that the probability of civilization surviving to the end of this century is no more than 50%. 50-50, a coin flip. Coming from a man who had spent 4 decades studying the large-scale structure of the universe, this was not casual speculation. It was a considered assessment from one of the most qualified scientists on Earth. He was so confident in this assessment that he made a public wager registered with the Long Bet Project. He wagered $1,000 that by the year 2020, an instance of bioerror or bioterror would have killed 1 million people. The bet was made in 2002. COVID-19 arrived in late 2019. The death toll exceeded 1 million by September 2020. The origins remain debated. The body count does not. Rees focused heavily on what he called the new threats, not asteroid impacts, not supervolcanoes, bioterrorism, engineered pathogens, nanotechnology, particle accelerator risks, which he acknowledged were extremely unlikely, but noted that the consequences of being wrong were total, and artificial superintelligence, which he identified as the longest-term concern, but potentially the most severe. By 2018, Rees had softened his language. He shifted from 50-50 extinction to concerns about civilizational setbacks, preferring catastrophic to existential. This partly explains the gap between his 50% and Ord's 17%. Rees uses a broader definition that includes major civilizational disruptions short of extinction. Ord applies the strict criterion of permanent, irreversible loss of humanity's long-term potential. The disagreement is more about definitions than about the actual level of danger. But notice the range. Carter's Doomsday argument suggests humanity ends sooner than we think. Gott's Copernican method gives us between 5,000 and 8 million years, with the median uncomfortably close to the present. The Drake equation, fed with modern data, predicts a galaxy full of civilizations that do not exist. The Great Filter says something destroys them. Ord calculates a 1 in 6 chance it happens to us this century. Rees says 50-50. 5 independent frameworks, developed by unrelated researchers in different decades, using different methods, and every one of them produces an answer in the same range. A range that says, this century, the century you are living in right now, is the most dangerous period in the history of our species. Not by a small margin, by an overwhelming one. That convergence is not a coincidence. And if you think it is abstract, if you think these are just numbers on paper, philosophical arguments, and probability tables that have no connection to the physical world you actually live in, then you need to hear what happened on the night of September 26th, 1983. Because the math is not abstract, the math has been tested. And on at least 4 occasions that we know of, the result was very nearly the one the equations predict. Shortly after midnight, on September 26th, 1983, Lieutenant Colonel Stanislav Yevgrafovich Petrov was sitting in a chair he was not supposed to be sitting in. Petrov was a software engineer, not a duty officer. He had helped write the code for the Soviet OKO early warning satellite system, but his regular replacement was unavailable. So Petrov had taken the shift at Serpukhov 1-5, a secret bunker south of Moscow that served as the nerve center of the Soviet Union's nuclear early warning network. His job was to watch 9 satellites that monitored American missile fields and report any launch detection to Soviet High Command. At 12:15 a.m., the screen in front of him lit up. One of the 9 OKO satellites, positioned in a Molniya orbit high above the United States, had detected a missile launch from Malmstrom Air Force Base in Montana. The word launch appeared in large red letters on the backlit screen. A siren began to wail. Petrov later recalled that the siren was so loud he could barely think. Soviet nuclear doctrine was clear. If American intercontinental ballistic missiles were detected, the response was immediate retaliation. The missiles would reach the Soviet Union in approximately 20 minutes. Every second of delay reduced the number of retaliatory weapons that could be launched before American warheads destroyed them in their silos. The system was designed for speed, not deliberation. Petrov's job was to confirm the detection and relay it up the chain of command. The chain terminated with the General Secretary of the Communist Party, who would authorize a full retaliatory strike. Then a second missile appeared on the screen, then a third, then a fourth, then a fifth. 5 American ICBMs launched from Montana, streaking toward the Soviet Union. Petrov had to make a decision. The system was telling him that nuclear war had started. 5 missiles were in the air. His superiors were waiting for confirmation. Soviet military doctrine, Soviet training, and Soviet technology were all telling him the same thing. This is real. Report it now. He did not. Petrov reported the detection as a system malfunction. He would later explain his reasoning in interviews. First, a real American first strike would be massive. Hundreds or thousands of missiles, not 5. 5 missiles made no strategic sense. Second, the OKO system was new, and he knew its software better than anyone. He did not trust it. Third, ground-based radar installations had not detected anything, though he knew ground radar had a shorter detection range and the missiles might not be visible yet. He sat in that chair for 23 minutes. 23 minutes during which, if he had followed protocol, a full Soviet nuclear counterattack would likely have been launched against the United States and NATO. The cause of the false alarm was later identified as a rare alignment of sunlight reflecting off high-altitude clouds near the border of the Soviet early warning satellite's field of view. A trick of light. 5 phantom missiles conjured from reflected sunshine. Petrov was initially praised by his commanding officer. Then, he was reprimanded for failing to fill out his paperwork correctly during the incident. He was reassigned. He suffered a nervous breakdown. His wife did not learn what had happened for 10 years. He lived the rest of his life in a small apartment in Fryazino, a town northeast of Moscow. He died on May 19, 2017, at the age of 77. Most of the world did not learn of his death for months. Think about the math for a moment. Petrov's decision was one data point, one night, one officer, one set of circumstances. And the outcome depended entirely on the fact that the officer on duty happened to be a software engineer who distrusted his own system. If the regular duty officer had been in that chair, someone trained to follow protocol rather than question it, the calculation changes. The 23 minutes disappear. The report goes up the chain. And in September 1983, the Soviet leadership was already in a state of extreme paranoia. Yuri Andropov, the General Secretary, was convinced that the United States was planning a first strike. He had launched Operation Rayan, the largest peacetime Soviet intelligence gathering operation in history, specifically to detect preparations for a nuclear attack. Into that environment, a confirmed satellite detection of 5 American missiles would have been treated as exactly what Andropov feared. But Petrov was not the closest call. To find that, you have to go back 21 years earlier, to the Caribbean. On October 27, 1962, the 13th day of the Cuban Missile Crisis, the Soviet diesel-electric submarine B-59 was running deep in the Sargasso Sea near Cuba. It was one of 4 Foxtrot-class submarines that the Soviet Navy had dispatched to the Caribbean, and it was carrying a weapon that the Americans did not know about. In addition to its conventional torpedoes, B-59 had a single T5 nuclear torpedo with a yield of approximately 10 kilotons, 2/3 the size of the Hiroshima bomb, enough to vaporize an aircraft carrier and every ship within a mile of it. The crew had been submerged for days. They had lost radio contact with Moscow. They did not know whether war had already started on the surface. The conditions inside the submarine were unbearable. Air conditioning had failed. Internal temperatures reached 37 degrees Celsius. Carbon dioxide levels were rising. Sailors were fainting at their stations. The batteries were dying. And above them, 11 American destroyers and the aircraft carrier USS Randolph had detected the submarine and were dropping practice depth charges, signaling grenades designed to force the sub to surface and identify itself. The crew did not know these were practice charges. They sounded exactly like the real thing. The explosions shook the hull. Captain Valentin Savitsky, exhausted and convinced that hostilities had begun, ordered the nuclear torpedo armed. His words, as reported by Signal's intelligence officer Vadim Orlov, who was aboard: "Maybe the war has already started up there while we are doing somersaults down here. We are going to blast them now. We will die, but we will sink them all. We will not become the shame of the fleet." Soviet naval protocol required the agreement of 3 officers to authorize a nuclear torpedo launch: the captain, the political officer, and, on this particular submarine, the commander of the entire submarine flotilla, who happened to be aboard B-59 for this deployment. Captain Savitsky wanted to fire. Political officer Ivan Maslenikov agreed. The authorization of all 3 officers was required. The flotilla commander was Vasily Alexandrovich Arkhipov. He was 36 years old. The previous year, he had served as deputy commander aboard K-19, a nuclear submarine whose reactor had suffered a catastrophic coolant failure. Arkhipov had watched his crewmates absorb lethal doses of radiation while jury-rigging repairs to prevent a full meltdown. Several died within weeks. Others, including Arkhipov himself, suffered long-term radiation exposure effects that would shadow the rest of his life. He knew what nuclear weapons did, not theoretically, physically, in the bodies of men he had served beside. Arkhipov refused. He argued that if war had truly broken out on the surface, the Americans would not be fixating on a single diesel submarine. They would be prosecuting a full-scale naval campaign. The depth charges were a provocation, not an attack. He persuaded Savitsky, who was half mad from heat and exhaustion and CO2 deprivation, to surface instead of firing. B-59 surfaced. The Americans surrounded it. The confrontation ended without violence. The crisis, the closest the world has ever come to nuclear war, was resolved 6 days later when Kennedy and Khrushchev reached an agreement. The Americans did not learn that Soviet submarines in the Caribbean had been carrying nuclear torpedoes until Soviet archives were partially opened decades later. At a 2002 conference in Havana, marking the 40th anniversary of the crisis, Thomas Blanton of the National Security Archive told the assembled participants what the newly declassified documents revealed. The room went silent. One participant called Arkhipov the guy who saved the world. Arkhipov never spoke publicly about the incident. He never told his family. He returned to the Soviet Navy, rose to the rank of Vice Admiral, and retired. He died on August 19th, 1998, at the age of 72, of kidney cancer, almost certainly linked to the radiation exposure from K-19. His wife Olga learned the full story only after his death. She said simply, "He is the man who saved the world." 2 men who saved the world. One of them was reprimanded and had a nervous breakdown. The other died of cancer. Neither was recognized during their lifetime. The system that nearly killed everyone continued operating exactly as designed. The lesson is not that the system has safeguards. The lesson is that the safeguards are individual human beings who happened to make the right call under conditions that were specifically designed to make the wrong call seem rational. But Petrov and Arkhipov are not even the full picture from that period, because 36 days after Petrov's incident, still in 1983, NATO launched a command post exercise called Able Archer 83. The exercise, which ran from November 2nd through the 11th, simulated an escalation from conventional warfare to nuclear release. In previous years, these exercises had been routine, but in 1983, Able Archer incorporated new features that made it nearly indistinguishable from the real thing. New coded communication formats, radio silence procedures, simulated nuclear weapon release authorization procedures, and, for the first time, participation by heads of government. These were precisely the indicators that Operation Ryan was designed to detect. On November 8th or 9th, Moscow Center sent a flash telegram to every KGB and GRU intelligence station worldwide, reporting that an American nuclear alert appeared to be underway. Soviet fighter aircraft armed with nuclear weapons were placed on alert in East Germany and Poland. Military units in the Baltic and Czechoslovakia were brought to increased readiness. The West did not know how close things had gotten until Oleg Gordievsky, a KGB colonel who had been secretly working for British intelligence since 1974, reported the Soviet reaction to London. His intelligence reached Prime Minister Thatcher and was passed to President Reagan. Reagan wrote in his diary on November 18, 1983, "I feel the Soviets are so defense-minded, so paranoid about being attacked, that without being in any way soft on them, we ought to tell them no one here has any intention of doing anything like that." It was one of the pivotal moments that eventually led to the softening of the Cold War, but it happened after the crisis was over. During the crisis, neither side knew how close the other was to launching. An exercise simulating nuclear war nearly caused nuclear war, not because anyone wanted it, not because any individual made a reckless decision, because the systems, the intelligence apparatus, the detection networks, the command structures, the doctrines were designed in a way that made accidental escalation structurally possible. Petrov could say no, but Able Archer did not have a Petrov. It had systems talking to systems, each one interpreting the other's signals through a lens of maximum threat. But there is an incident that is in some ways more terrifying than either of these, because it did not involve any decision at all. On January 24, 1961, a B-52G Stratofortress carrying two Mark 39 thermonuclear bombs broke apart in midair over Goldsboro, North Carolina. Each bomb had a yield of 3.8 megatons, 260 times the bomb dropped on Hiroshima. Both weapons separated from the aircraft. Both began their arming sequences as they fell. On one of the bombs, 3 of 4 safety mechanisms failed. 3 out of 4. A single low-voltage switch, the last of 4 independent safety devices, prevented a thermonuclear detonation over the American East Coast. A declassified Sandia National Laboratories report, not made public until 2014, confirmed the extreme danger. Secretary of Defense Robert McNamara said privately that the Goldsboro incident was the closest the United States had come to an accidental nuclear detonation. The other bomb's thermonuclear secondary stage, the component that would have produced the full 3.8 megaton yield, was never recovered. It is still buried in the muddy farmland of Wayne County, North Carolina. The Air Force purchased an easement on the land and monitors it periodically for radioactivity. It has been there for over 60 years. There is one more incident that deserves your attention, because it demonstrates that the margin did not widen after the Cold War ended. On January the 25th, 1995, a black Brant 12 sounding rocket was launched from Andøya Rocket Range in Norway to study the Northern Lights. Norway had notified Russia of the launch in advance, but due to a bureaucratic failure, the notification never reached the Russian radar operators who detected the rocket. What they saw on their screens looked like a submarine-launched Trident missile on a trajectory consistent with an electromagnetic pulse attack designed to blind Russian radar before a full-scale nuclear strike. President Boris Yeltsin was alerted. The Shchejet, the Russian nuclear briefcase, was activated. For the first time in the history of the Russian Federation, the nuclear launch codes were made available to the president in response to a perceived incoming attack. Yeltsin later confirmed this publicly. "I have indeed used yesterday for the first time my little black case with a button that is always with me," he said. Russian officers tracked the rocket for several minutes before determining it was heading away from Russian territory. The alert was stood down. The world continued. But for those minutes, a weather research rocket launched to study the aurora borealis had activated the nuclear launch apparatus of a nation with thousands of warheads. In 1995, 4 years after the Soviet Union had ceased to exist, Now apply the math. Martin Hellman, a Stanford professor who co-invented public key cryptography and spent years analyzing nuclear deterrence as a risk problem, estimated the annual probability of full-scale nuclear war at somewhere between 0.02% and 0.5% per year. Barrett, Baum, and Hostetler, writing in Science and Global Security in 2013, narrowed this and estimated the annualized probability of inadvertent nuclear war between the United States and Russia at approximately 2%, with a 90% confidence interval spanning 0.02 to 7%. They noted that roughly half the risk exists during peacetime, from system faults, miscalculations, and incidents like the ones you just heard about. 2% per year sounds small. It is not small. The cumulative probability formula is simple. The probability of surviving 1 year is 0.98. The probability of surviving 100 years is 0.98 raised to the 100th power. That equals 0.13, a 13% chance of making it through the century without an inadvertent nuclear war between the United States and Russia alone. An 87% chance that it happens at Hellman's more moderate 1% annual estimate. The century-long probability of nuclear war is still 63%. These are not numbers anyone wants to see. They are published in peer-reviewed journals, and the near misses are not evidence that the system works. The near misses are evidence that the margin is thin enough to depend on whether the right person happens to be sitting in the right chair at the right moment. Petrov was a software engineer who did not trust his own system. Arkhipov was a submarine officer who had survived a reactor accident and knew what radiation does to the human body. Yeltsin hesitated for a few minutes over a sounding rocket. These are not safety features. These are accidents of biography that happened to break our way. I said there were at least 4 incidents we know of. That qualifier matters. These are the ones that were eventually declassified or reported. The ones where someone survived to tell the story or where documents were eventually released. The number of close calls that remain classified or that were never documented or that occurred in countries with less transparent military establishments is not known. It is not zero. The math predicts danger, and the history confirms that the danger is real, that it is not theoretical, that the distance between the equations and the actual end of civilization has been, on multiple documented occasions, a single human decision or a single mechanical switch. But all of those incidents involve nuclear weapons, Cold War technology, 70-year-old bombs. Surely the danger has peaked. Surely the modern world is safer. It is not, and the reasons it is not safer are the reasons that Ord puts at the top of his table, the threats that did not exist when Petrov sat in his chair, the threats that do not have a Petrov because there is no chair to sit in, and no screen to watch, and no 23 minutes to think. In July 2024, Ord published an update called The Precipice Revisited, in which he reassessed his original estimates in light of 4 years of developments. His climate risk estimate moved down. Global emissions were tracking below the worst-case scenario, and the IPCC had narrowed its estimate of equilibrium climate sensitivity, making the most catastrophic warming outcomes less likely. But his nuclear risk estimate moved up, driven by the Russia-Ukraine war and the approaching expiration of New START. His AI risk estimate, already the highest in the table, did not change in a way that shifted the order of magnitude. But Ord noted that capabilities had advanced faster than he expected, and alignment research had not kept pace. None of his rounded estimates changed enough to alter the overall picture. The 1 in 6 stood. But what the update revealed, more than any specific change, was the compounding nature of the danger. The old threats do not go away when new threats arrive. Nuclear weapons do not become safe because AI is dangerous. Engineered pathogens do not become less feasible because nuclear arsenals are unregulated. Each new risk category adds to the total, and the interactions between categories can be worse than the sum of the parts. An AI system that assists in the design of novel pathogens, a nuclear crisis escalated by autonomous decision-making systems, a pandemic that weakens global governance enough to make nuclear proliferation easier. The risks are not a list. They are a network, and the network is densifying in real time. The nuclear arsenals have not gone away. Let me be specific about this, because the assumption that the Cold War ended and the danger receded is one of the most consequential mistakes a person living in the 21st century can make. The New START Treaty, a last remaining arms control agreement between the United States and Russia, expired on February 4th, 2026. It was not renewed. It was not replaced. For the first time in over half a century, there is no treaty of any kind constraining the nuclear arsenals of the world's two largest nuclear powers. The Bulletin of the Atomic Scientists moved the Doomsday clock to 85 seconds to midnight in 2026, the closest it has ever been, citing the treaty's expiration alongside the war in Ukraine and the acceleration of AI development. Russia possesses approximately 5,900 warheads. The United States possesses approximately 5,500. China is rapidly expanding its arsenal, with the Pentagon estimating over 500 warheads by 2030, up from roughly 200 in 2019. The United Kingdom, France, India, Pakistan, Israel, and North Korea possess the rest. The total global inventory is approximately 12,500 nuclear warheads. Some of them are on hair trigger alert, meaning they can be launched within minutes of a command. The Cold War ended. The weapons did not. But nuclear weapons are the legacy threat. They are the danger we have, against all probability, survived for 80 years. What makes this century different? What makes Ord's estimate of 1 in 6 credible in a way it would not have been in 1960 is the arrival of entirely new categories of existential risk that compound the nuclear danger rather than replacing it. Start with the one Ord ranks second: engineered pandemics, 1 in 30 per century. In 2019, Kevin Esvelt, a professor at MIT and one of the developers of CRISPR gene drive technology, testified before Congress about the state of biosecurity. His testimony included a demonstration that should have triggered a national emergency and did not. Esvelt's team, working with FBI approval, used a pseudonym to order fragments of DNA encoding parts of the 1918 influenza virus from commercial DNA synthesis companies. The 1918 flu killed somewhere between 50 million and 100 million people. In an era before global air travel, before a world of 8 billion people connected by 50,000 daily flights, 36 out of 38 companies shipped the DNA, no questions asked. Enough material to reconstruct the virus 3 times over, using a fake name. Esvelt subsequently co-founded Secure DNA, a non-profit that provides free screening tools to DNA synthesis companies, and the Nucleic Acid Observatory, which monitors wastewater for novel biological threats. Both are operating on shoestring budgets. Both are trying to patch a security gap that the federal government has not yet meaningfully addressed. The institutional infrastructure that is supposed to prevent biological weapons is, to put it politely, inadequate. The Biological Weapons Convention, the international treaty banning the development and stockpiling of biological weapons, has been in force since 1975. 187 states are party to it. It has no verification mechanism. None. The Chemical Weapons Convention, as the Organization for the Prohibition of Chemical Weapons, with an annual budget of approximately $94 million and the authority to conduct inspections. The Nuclear Non-Proliferation Treaty has the International Atomic Energy Agency, with a budget exceeding $700 million, and inspectors stationed around the world. The Biological Weapons Convention has an implementation support unit with a staff of 4 people operating on approximately $1.4 million a year, less than the operating budget of a mid-range restaurant. In 2001, the international community attempted to negotiate a verification protocol for the BWC. Inspections, declarations, accountability mechanisms, the kind of basic institutional infrastructure that the chemical weapons and nuclear non-proliferation regimes have had for decades. The United States, under the George W. Bush administration, unilaterally withdrew from the negotiations. It was the only country to oppose the verification protocol. The reason given was that inspections could compromise proprietary pharmaceutical and biodefense research. The protocol has never been revived. Esveld can order pandemic-capable DNA under a fake name. The treaty that is supposed to prevent biological weapons has no way to verify compliance. The total global spending on biological weapons prevention is a rounding error in the defense budgets of the nations most likely to be targeted. To put the scale of the underfunding in perspective, the United States alone spends over $800 billion per year on defense. The entire global apparatus for preventing the development of biological weapons that could kill billions of people operates on less than 2 million. If you divide the BWC's budget by the number of states party to the treaty, each nation's share comes to roughly $10,000 a year. That is not a rounding error. That is an insult to the concept of risk management. And Ord puts the probability of an engineered pandemic causing an existential catastrophe at 1 in 30 per century. Not because the pathogen itself would kill everyone, but because a sufficiently lethal and transmissible engineered agent could trigger civilizational collapse, breakdown of food systems, breakdown of governance, cascading failures that push humanity past the point of recovery. The 1918 flu killed 3 to 6% of the world's population with a pathogen that nature produced accidentally, a deliberately engineered pathogen designed for maximum lethality and transmissibility by someone with access to modern gene synthesis tools could do far worse, and the barrier to entry is falling every year. That is the number 2 risk on the table. Number 1 is something else entirely. In 2023, the landscape of artificial intelligence shifted in a way that caught even the people building the systems off guard. Large language models demonstrated capabilities that had not been anticipated at their scale. Reasoning abilities, planning abilities, the capacity to write code, to manipulate people, to pursue goals across extended interactions. The people at the frontier of this technology began saying things in public that they had previously only said in private. On May 1st, 2023, Geoffrey Hinton resigned from Google. Hinton is sometimes called the godfather of AI. He is one of the inventors of backpropagation, the algorithm that underlies virtually all modern neural network training. He shared the 2018 Turing Award with Yoshua Bengio and Yann LeCun. In 2024, he received the Nobel Prize in Physics for his foundational work on artificial neural networks. He left Google explicitly to speak freely about AI risk. His explanation was blunt. The idea that this stuff could actually get smarter than people. A few people believed that, but most people thought it was way off. I thought it was 30 to 50 years or even longer away. Obviously, I no longer think that. Hinton estimates the probability that AI causes human extinction at 10 to 20%. On May 30th, 2023, the Center for AI Safety published a single-sentence statement. Mitigating the risk of extinction from AI should be a global priority alongside other societal-scale risks, such as pandemics and nuclear war. Over 1,000 researchers and public figures signed, including Hinton, Bengio, Sam Altman of OpenAI, Demis Hassabis of Google DeepMind, and Dario Amodei of Anthropic. These are the people building the systems. They are signing statements, comparing their own technology to nuclear weapons and pandemics. The 2023 AI Impact Survey of 2,778 AI researchers found a median estimate of 5% for extremely bad outcomes from AI, meaning outcomes at the level of human extinction. The mean was 14.4%, pulled higher by a significant tail of researchers who assign much larger probabilities. 38% of respondents assigned at least 10% probability to extinction-level AI outcomes. A separate project called the Existential Risk Persuasion Tournament put the disagreement into even sharper relief. When AI domain experts were asked for their median estimate of AI-caused extinction risk by 2100, they gave 3%. When professional super forecasters, people who are demonstrably better than average at predicting future events, were asked the same question, they gave 0.38%. A nearly tenfold gap between the people who understand the technology and the people who are statistically best at predicting the future. Both groups were working from the same publicly available information. The disagreement is not about facts. It is about how much weight to give to scenarios that have no historical precedent. The super forecasters are trained to anchor on base rates. There is no base rate for artificial superintelligence. There has never been one. So the super forecasters default to unprecedented events are unlikely, and the domain experts default to you do not understand what this technology is going to become. Neither group can prove the other wrong, and the tenfold gap between their estimates is itself a measure of how poorly we understand a risk. The disagreement among individual experts is even wider. Eliezer Yudkowsky, who has spent over 2 decades working on AI alignment, estimates the probability of AI-caused human extinction at over 95%. Yann LeCun, Hinton's co-Turing laureate, estimates it at approximately 0. Stuart Russell, professor of computer science at Berkeley and author of Human Compatible, treats the risk as serious and credible without assigning a specific number, but has described superhuman AI as potentially the biggest event in human history, and perhaps the last. When the people building a technology cannot agree on whether it will cause human extinction with 95% probability or 0% probability, that disagreement itself is evidence. It is evidence that the technology is not understood well enough for anyone to be confident about the outcome. And the range of expert opinion, from near zero to near certain, is exactly what you would expect to see from a technology that is advancing faster than the theoretical understanding needed to predict its behavior. The institutional response has been rapid by the standards of international governance and glacial by the standards of the technology itself. The UK hosted the first Global AI Safety Summit at Bletchley Park on November 1st and 2nd, 2023, at the historic site where Alan Turing and his team broke the Enigma code during World War II. 28 countries and the EU signed the Bletchley Declaration, acknowledging the potential for serious, even catastrophic harm from frontier AI. AI safety institutes were established in the UK and the US. Follow-up summits occurred in Seoul in May 2024 and Paris in February 2025. Joshua Bengio chaired an international AI safety report backed by over 30 countries. These are good steps. They are not sufficient steps. The AI safety research community estimates that between 1% and 3% of AI research spending goes towards safety and alignment. Bengio and colleagues published in Science in May 2024, calling for at least 1/3 of AI research budgets to go towards safety. The gap between what is being spent and what the researchers themselves say should be spent is enormous, and the technology continues to advance during the gap. And then, there is the story of what happened to the institution that was supposed to study all of this. Nick Bostrom was born Niklas Bostrom in Helsingborg, Sweden, in 1973. He studied philosophy, physics, and mathematics before completing his PhD at the London School of Economics. As a graduate student, he moonlighted on the London stand-up comedy circuit, which is the kind of biographical detail that seems irrelevant until you consider the absurdist quality of what happened to his life's work. In 2005, Bostrom founded the Future of Humanity Institute at the University of Oxford. FHI was for nearly 2 decades the world's premier research centre for existential risk. It grew from 3 researchers to roughly 50 at its peak. Its alumni include Toby Ord and Anders Sandberg. It helped germinate the concepts that are now central to global discourse, including existential risk as a rigorous field of study, effective altruism, long-termism, AI alignment, information hazards, the unilateralist's curse. Bostrom's personal intellectual output is staggering. The simulation argument, the Doomsday argument formalization, global catastrophic risks, co-edited with Milan Cirkovic, and in 2014, Superintelligence, Paths, Dangers, Strategies, a book that became a New York Times bestseller and was read by Elon Musk, Bill Gates, and Sam Altman, all of whom cited it as formative in their thinking about AI risk. When the people building the most powerful AI systems in the world point to a single book that shaped their understanding of the danger, and that book came out of FHI, the Institute's importance is difficult to overstate. FHI was destroyed by bureaucracy. Starting around 2020, the Faculty of Philosophy at Oxford imposed a freeze on fundraising and hiring at FHI. The Institute had external funding, it had willing donors, it had researchers who wanted to join. The faculty would not allow it. The reasons were never fully public. But the friction between FHI's interdisciplinary, high-profile, externally funded model and the faculty's traditional academic structure had been building for years. In late 2023, the faculty decided not to renew the remaining staff contracts. The Future of Humanity Institute closed on April 16, 2024, after 19 years. Bostrom's words for it were death by bureaucracy. Anders Sandberg, one of FHI's longest-serving researchers, described the process as gradual suffocation by faculty bureaucracy and created a sardonic unit of measurement. 1 Oxford equals the amount of work required to read and write 308 emails. The institution that studied civilizational collapse was destroyed by an institution that could not be bothered to understand what it studied. If you wanted to design a metaphor for humanity's approach to existential risk, you could not do better. The closure coincided with personal scandal. In January 2023, a 1996 listserv email resurfaced in which Bostrom had written racist content. He posted an apology on his website, but made statements that some interpreted as defending eugenics. Oxford launched an investigation. The Guardian connected FHI's closure to broader scandals in the effective altruism community. The institution's end was messy, political, and entirely preventable, which is perhaps the most fitting possible ending for a story about whether humanity can coordinate to prevent its own destruction. The point is not whether Bostrom is a good person. The point is what his institute's closure tells you about the institutional capacity of the human species to address the very risks that the mathematics says will determine whether we survive. The world's leading existential risk research center was not defunded because its work was wrong. It was not shut down because the threats it studied turned out to be imaginary. It was killed by a philosophy department's hiring committee while the clock ticks. Now step back and look at the full picture. The nuclear arsenals are unconstrained for the first time in half a century. An MIT professor can order pandemic-capable DNA under a fake name. The International Biological Weapons Treaty has no verification mechanism because one country vetoed it. The people building the most advanced AI systems in the world sign public statements comparing their technology to nuclear weapons. The researchers studying these risks have their institute closed by administrative politics, and the total combined spending of every government on Earth on existential risk prevention is less than the budget of a single mid-sized city's fire department. Every framework, every equation, every risk table, every historical near-miss, every survey of the people building the most dangerous technology in human history points to the same window. This century, this generation, this window, not some far-off hypothetical period when humanity finally develops interstellar travel and has to worry about alien contact or galactic warfare. Now, and the Great Filter predicts that no civilization survives this window. That is what the silence means. The reason there are no signals from other civilizations, the reason the Drake equation's optimistic prediction collides with Fermi's empty sky, is that the transition from developing world-ending technology to developing the wisdom to survive it is a passage that virtually no civilization in the history of the universe has ever successfully made. The silence of the cosmos is not a mystery awaiting some clever resolution. It is a result, a measured, observed, confirmed result. And Ord's 1 in 6 is not a separate data point from that silence. They are the same data point, measured from different distances. Ord is measuring the filter from inside it. Fermi is observing its product from outside. You are inside the filter, right now, reading this, living in the century that the math says is the most dangerous one your species will ever face, if it faces any others at all. There is a mathematical concept called convergence, when multiple independent methods of estimation, using different assumptions, different data, and different theoretical frameworks, all produce answers in the same range. The convergence itself is evidence, not evidence that any single method is correct. Evidence that the methods are all detecting the same underlying reality. When your bathroom scale, your doctor's scale, and your friend's bathroom scale all say you weigh roughly the same amount, the convergence is telling you something. It is telling you that the number is real. What I have shown you over the last hour is a convergence, and I want to be precise about what makes it unusual, because convergences of this type are rare in any field, and in a field as uncertain as existential risk, this one should not exist. But it does. Brandon Carter, in 1983, used Bayesian statistics applied to birth rank. No data about technology, no data about nuclear weapons, no data about artificial intelligence, no knowledge of the Drake equation's implications. Pure probability theory applied to the observation that you exist and that your birth rank has a specific value. His result was that humanity ends much sooner than our intuitions suggest. The posterior probability strongly favors a total human population in the hundreds of billions, not the trillions. J. Richard Gott, in 1993, used the Copernican principle, a completely different philosophical starting point from Carter. No Bayesian updating, no birth rank, just the assumption that there is nothing special about the present moment. His result was that at 95% confidence, Homo sapiens survives between 5,000 and 8 million more years. The median is roughly 200,000 years. Applied to technological civilization specifically, which has existed for roughly 80 years, if you date it from the first nuclear test, the 95% confidence interval gives us between 2 more years and 3,120 more years. The median is 80 years. We are at the median right now. Frank Drake, in 1961, used an estimation framework for the number of detectable civilizations. His equation, with modern astronomical data, predicts thousands of civilizations in the Milky Way. Enrico Fermi, in 1950, observed that the galaxy appears to contain 0. The discrepancy between Drake's prediction and Fermi's observation is not a gap in knowledge. It is a data point. Something is preventing the predicted civilizations from existing or persisting long enough to be detected. The most straightforward interpretation is that L, the longevity of technological civilizations, is short, very short. Short enough to explain the silence across 13 billion years and 200 billion stars. Robin Hanson in 1998 translated the Fermi observation into a filter framework. If the early biological steps are easy, the filter is ahead. The evidence from extremophile biology, exoplanet surveys, and amino acid detections in interstellar gas suggests the early steps are easy. Therefore, the filter is ahead. The filter operates at or near our stage of technological development. Virtually no civilization survives it. Toby Ord, in 2020, independently calculated the probability of existential catastrophe this century using Bayesian methods informed by domain expertise. 1 in 6. The dominant risk categories are technologies that have existed for less than a century. The risk from unaligned artificial intelligence alone, at 1 in 10, exceeds the combined risk from every natural hazard on the planet by 4 orders of magnitude. Martin Rees, in 2003, estimated the probability of civilizational survival at no more than 50%. He arrived at this figure through a different methodology than Ord, with different emphasis on different risk categories, but the same order of magnitude. The 2023 survey of 2,700 AI researchers found a median 5% extinction risk from AI alone. with a mean of 14.4%. The cumulative probability models for nuclear war, based on documented near misses and the annual frequency of crisis events, produce century-long probabilities ranging from 63 to 87%, depending on the assumed annual rate. These are not the same method. They are not the same researchers. They are not the same decades, the same countries, the same fields, or the same assumptions. A Bayesian statistician in Cambridge, a cosmologist at Princeton, an astronomer in West Virginia, and a physicist at Los Alamos, an economist at George Mason, a philosopher at Oxford, an astrophysicist who runs the Royal Society. Thousands of AI researchers surveyed anonymously, and a cumulative probability model built from declassified military incidents. They all land in the same territory, single-digit to double-digit percentage probability that human civilization ends this century. Not in 1,000 years, not in 1,000,000 years, this century, the one you are in. That convergence demands an explanation, and the explanation is the one I have been building toward since the first minute of this video. They are not converging because they copied each other. Carter did not know about the Drake equation's implications for civilizational survival. Gott did not reference Hanson's filter. Ord did not derive his numbers from Fermi's silence. They are converging because they are all measuring the same thing. They are measuring the filter. The filter is not a single event. It is a phase. It is the period between a civilization developing the technology capable of destroying itself and that civilization developing the institutional wisdom, the coordination mechanisms, the governance structures, the cultural maturity necessary to survive its own capabilities. The nuclear test is the beginning of the phase. The development of engineered pathogens extends it. The creation of superhuman artificial intelligence, if and when it occurs, may be its culmination. The phase has a duration, and the mathematical models, all of them, are telling you that the duration is roughly 1 century, give or take. This maps onto Hanson's filter with disturbing precision. Step 8 on his ladder is where we are now. Tool using animals with big brains and world-ending technology. Step 9 is a colonization explosion. Visible evidence of a spacefaring civilization. The gap between Step 8 and Step 9 is where civilizations die. And the gap, measured from inside it, is the period Ord is quantifying in his table. 1 in 6. 1 in 10 from AI alone. 1 in 30 from engineered pandemics. 1 in 1,000 from nuclear war. These are not independent risks that coincidentally add up to a frightening total. They are components of the filter. They are the mechanisms by which the universe empties itself of intelligence. Let me return to Brandon Carter, the man who started this. Carter is now in his early 80s, working at the Paris Modon Observatory. He spent the first half of his career helping to prove the no-hair theorem for black holes, deriving the mathematical tools that Roger Penrose and Stephen Hawking used to map the causal structure of space-time. He proposed the anthropic principle at a celebration of Copernicus. He later regretted the name. He said the word anthropic made it sound like the principle was about humans, when really it was about the constraints that any observer's existence places on what they can observe. In 1983, he applied that principle to the observation that he, Brandon Carter, existed, and that his birth rank among all humans was a specific number, and the math told him something he could not publish. Not because it was wrong, not because it lacked rigor, because it was the kind of answer that changes how you see everything else. If the Doomsday argument is correct, even approximately, its implications extend far beyond one species on one planet. Every civilization that has ever evolved intelligence anywhere in the observable universe was inside the same statistical structure. Each of them had observers with birth ranks. Each of them could have run Carter's calculation. And for each of them, the math would have said the same thing. You are probably not at the beginning of your civilization story. You are probably somewhere in the middle. And the middle means the end is not as far away as you want it to be. Carter's personal reluctance to publish was, in hindsight, an early instance of the pattern that defines this entire field. The math is clear, the implications are terrifying, and the human response, from individuals and institutions alike, is to look away. Carter did not publish. The physics community treated the Doomsday argument as a curiosity for 20 years. Gott's predictions were verified and then ignored. Rees's 50-50 claim was treated as provocation rather than analysis. Ord published his table and the world kept scrolling. Hinton resigned from Google and the stock price went up. FHI was shut down by a philosophy department. The Biological Weapons Convention cannot afford a staff of 5, and the New START Treaty expired without a replacement. Each of these facts, taken individually, can be explained away. Carter was too cautious. Gott was too heterodox. Rees was too pessimistic. Ord's methodology was too subjective. Hinton was overreacting. FHI had management problems. The BWC is a diplomatic backwater. New START was a victim of geopolitical timing. But taken together, they form a pattern. And the pattern is that whenever the mathematics of existential risk produces a clear and quantitative result, the institutions responsible for acting on that result find a reason not to. The math gets published. The math gets verified. And then the math gets filed away. Not suppressed, not censored, just quietly moved to the bottom of the priority list by people who have more immediate things to worry about: budgets, elections, faculty politics, quarterly earnings. This is, arguably, the filter in action. Not a dramatic cataclysm, not a single moment of recklessness. A slow, distributed, structural inability to respond to threats that are large in magnitude but uncertain in timing. The filter does not need to be a war or a plague or a machine uprising. The filter can be the simple fact that human institutions are not built to process century-scale risks with 5 to 50% probabilities. They are built to process immediate crises with clear causes and identifiable enemies. And existential risk is neither immediate, nor clear, nor caused by an identifiable enemy. It is caused by the aggregate behavior of a civilization that is smart enough to build world-ending technology and not yet wise enough to govern it. Hanson wrote in his original essay that optimism about our future is directly pitted against optimism about the ease of previous evolutionary steps. I want to restate that in terms the Convergence makes unavoidable. Optimism about our future is directly pitted against the silence of the cosmos. You can believe that humanity will solve AI alignment, prevent engineered pandemics, maintain nuclear deterrence indefinitely, and build the governance structures necessary to survive the next 80 years. Or you can believe that the Drake equations predicted thousands of civilizations should exist. You cannot believe both, because if civilizations routinely survive the filter, the galaxy should be colonized. It is not. The absence of evidence is, in this case, evidence. The silence is a measurement. And the measurement says that civilizations at our stage of development do not, as a rule, make it to step 9. There is one more piece of the math that I want to leave you with, and it concerns Gott's delta T argument applied not to Homo sapiens as a biological species, but to technological civilization as a phase of development. Gott's method is agnostic. It does not care what you are measuring. It only asks how long the thing you are observing has existed so far, and then produces a confidence interval for how much longer it will last. The formula is symmetrical and has been validated across hundreds of independent tests. Technological civilization, defined as the period during which humanity possesses the capability to destroy itself, began on July 16th, 1945, with the Trinity nuclear test in the New Mexico desert. As of today, that is roughly 80 years. Gott's formula, at 50% confidence, says technological civilization will last between 27 more years and 240 more years. At 95% confidence, between 2 more years and 3,120 more years. The median, the 50-50 point, the value where it is equally likely that we have more time remaining or less, is 80 years. 80 years from now, roughly the year 2105. That number was not derived from any assessment of nuclear arsenals, AI capabilities, biosecurity gaps, or institutional failures. It was derived from nothing but the Copernican principle and the current age of the thing being measured. It knows nothing about the specific risks. And it agrees with Ord. It agrees with Rees. It agrees with the Fermi observation. It agrees with the near-miss data. It agrees with the AI researcher surveys. The convergence is complete. I want to return one last time to the Green Bank Conference in November of 1961. 10 men in a remote observatory in the mountains of West Virginia discussing whether anyone else is out there. At the end of the meeting, Otto Struve raised a glass. "To the value of L," he said, "may it prove to be a very large number." L is the longevity of a technological civilization. It is the last variable in the Drake equation. It is the only variable that depends on what a civilization does with the knowledge it has gained. Every other variable is set by physics and biology. L is set by choice, by governance, by whether the species that builds the bomb also builds the institutions to survive the bomb, by whether the species that creates artificial superintelligence also solves the alignment problem, by whether the species that engineers pathogens also builds the surveillance systems and international treaties necessary to prevent their release. L is not a fact about the universe. It is a fact about us. And every measurement we have, from Carter's birth rank, to Fermi's silence, to Ord's table, to the documented near misses, to the Doomsday clock now ticking at 85 seconds to midnight, suggests that L is not a very large number, for us or for anyone. Struve died 2 years after the Green Bank Conference. He never learned the answer to his toast. Frank Drake spent the remaining 6 decades of his life listening. He died on September 2nd, 2022, at the age of 92. He never heard a signal. Nobody has. The radio dial is as silent today as it was when Drake first pointed that 85-foot dish at Epsilon Eridani in 1960. The equation Drake wrote on that chalkboard 65 years ago was supposed to be theoretical, a framework for organizing ignorance, a way to structure a conversation among 10 people in a room in West Virginia. But when you solve it with modern numbers, when you feed it the Kepler data on planetary frequency and the extremophile data on the resilience of biology and the exoplanet data on habitable zones, and then you hold the answer up against the observed silence of the cosmos, the equation stops being theoretical. The answer becomes real, and the answer is L. Every framework converges on L. Every equation resolves to L. The Doomsday argument is a statement about L. The Great Filter is a statement about L. The Fermi Paradox is an observation of L across the entire galaxy. Ord's table is a decomposition of the threats that determine L for our specific civilization in this specific century. The near misses are empirical measurements of how close L has already come to zero for us. You are living inside L. You have been your entire life. The question is whether L, for this civilization, on this planet, in this century, is large enough to include whatever comes next. Whatever comes after the weapons and the pathogens and the algorithms and the institutional failures and the expired treaties and the 85 seconds on the clock. The math does not answer that question. The math tells you the odds. 1 in 6, according to Ord. 50-50, according to Rees. 5% from AI alone, according to the median of the people building AI. 80 years at the median, according to Gott's Copernican method. 0 detectable civilizations, according to 60 years of radio observation. A single low-voltage switch in Goldsboro. A single lieutenant colonel in Serpukhov. A single submarine officer in the Caribbean. 85 seconds on the Doomsday clock, and no treaty to replace the one that expired. The math tells you the odds. The rest is L.